Good morning, children. Sairam. Children, in the previous presentation, I'm sorry. In the previous presentation, we have discussed about the bond order. I have told you we have discussed all the bond parameters and we have discussed bond order also. Now, after that, in the live class, we have started with the valence shell electron pair repulsion theory. We'll complete it in the live class. I'm starting with resonance now. Now, children, what is resonance? See, you all must have seen that many a time there are certain molecules which are having two different structures or more than two structures. Actually, it is often observed that one single level structure is inadequate for the representation of all the properties of a molecule. Such molecules require more than one structure to define all the properties and are said to exhibit resonance. So, how will you define resonance? You can say that when one single molecule is inadequate to explain all the properties of a molecule and more than one structures are required, such a molecule is said to exhibit resonance. In resonance, the multiple bond, or you can say the pi bond, starts moving. We are taking the example of ozone molecule first. Now, in ozone molecule, as you all can see, the chemical formula is O3. What happens? 3 oxygen atoms are there. 1, 2 and 3. 3 oxygen atoms are there. If I'll draw the Lewis electron dot structure, you all know all oxygen atoms are having 6 electrons in the outermost shell. Now 1, 2, 3, 4, 5 and 6. Similarly, this oxygen atom also have 1, 2, 3, 4, 5 and 6. And this oxygen atom will form a coordinate bond by sharing one electron pair with this oxygen atom. This bond is a coordinate bond. So 2 plus 2, 4, 5 and 6. Now, in this way they complete the valency. Now, if you check, all the oxygen atoms will have 8 electrons in the outermost shell. Now, children, that means the oxygen number 1 and 2 are connected through a single bond and oxygen number 2 and 3 are connected through a double bond. But when spectroscopical studies were done on the ozone molecule, it was found that both the bond, the bond between oxygen number 1 and 2 and the bond between oxygen number 2 and 3, both are equal. And in bond order, I have taught you that the single bond is longer and the double bond is shorter. But here both the bonds are equal. That means you can also show it like this. This bond is the coordinate bond and this bond is the double bond. So, it was later on observed that there can be a resonance hybrid of the two molecules. Now, what will be the resonance hybrid, you see? I hope you all are clear with the two structures. Now, see the resonance hybrid. In the resonance hybrid, one oxygen atom will be present here, oxygen number 2, oxygen number 3. Now, you are knowing that 2 oxygens are connected through a single bond and the other 2 are connected through a double bond. But actually, I am drawing one single bond here and the other single bond here. And there is a partial double bond character in both the bonds. That means the double bond sometimes shifts to this side and sometimes it shifts to this side. And both the bond are having the bond length of 128 pm. pm means 10 raised to the power minus 12. Similarly, the other bond is also having the bond length of 128 picometer. So, how will you define resonance? You will say that when one single molecule is incapable to express all the properties of a molecule and more than one structures are required, such a molecule is said to exhibit a resonance, like for example in case of the ozone molecule. Now another example I am taking, that is carbon dioxide molecule. In carbon dioxide, as it is clear from the formula of carbon dioxide that there is one carbon atom in carbon dioxide molecule and two oxygen atoms. Now children, many a times the structure is like this, double bonds. Many a time the structure is like this, triple bond here and a single bond here. Now sometimes the structure can be drawn like this, triple bond here and a single bond here. So these three molecules will represent, these are the resonating structures you can say, or the canonical forms. You can also call them as the canonical forms. So these are the three resonating structures of carbon dioxide molecule. Children, in general, you can say that resonance stabilizes the molecule. In resonance, the multiple bond shifts from one position to another. It provides stability to the molecule, and the resonance averages the bond characteristics as a whole. That means it equates all the bond and it averages the bond characters. Now coming to the next important topic, that is polarity of bonds. Now you all must be knowing the meaning of the word polar. What is polar? Polar means having poles. Poles are either positive pole or a negative pole. Now children, in the beginning of the chapter I have explained you about the ionic character and the covalent character of the bond, but actually in actual practice if we see, none of the bond is 100% ionic or 100% covalent. Even in case of the covalent bond between two hydrogen atoms, there is some ionic character. So when a covalent bond is formed between two similar atoms like hydrogen, two hydrogen atoms, two oxygen atoms, two chlorine atoms, two nitrogen atoms or two fluorine atoms, the shared pair of electron is equally attracted by the two atoms. As a result, the electron pair is situated exactly between the two identical nuclei. We call it to be a non-polar covalent bond, but it is having some ionic character also. Now, if we are having heteronuclear molecules like hydrogen and fluorine, you all know that there is a great difference of electronegativity between hydrogen and fluorine. The shared pair of electron between the two atoms get displaced towards the fluorine atom. This is hydrogen atom, this is bond, and this is fluorine. You all know fluorine being more electronegative. There is a far difference. You can say fluorine is far more electronegative than hydrogen. So what happened? The shared pair of electron shifts towards fluorine. As a result, the covalent bond becomes polar, and now it is called a polar covalent bond. Now such a molecule possesses a dipole moment. Now what is dipole moment? See, it can be defined as the product of magnitude of charge and the distance between the center of positive and negative charge. See, the dipole moment, it is denoted by mu, and it is equal to charge, that is denoted by Q, multiplied by the distance of separation denoted by R. Now see, as distance is involved, it is a vector quantity because direction is involved and depicted by the small arrow with the tail on the positive charge and the head pointing towards the negative charge. Like for example, in case of hydrogen fluoride HF, this is the bond. Now here are the shared pair of electrons. Now how will we show the dipole moment? This is the direction of the dipole moment. That means there's a small arrow with the tail on the positive charge. This hydrogen is having positive charge, and the head on the negative charge, where fluorine is having the negative charge. Now here there will be some resultant dipole also. Now children, you have to remember that the unit to measure the dipole is, you all know, charge is coulombs and distance is meter. So it will be coulomb meter. Simply it is called D. It is actually equal to cm. C is for coulomb, m is for meter. Now children, another example we can take in case of the water molecule. In case of water molecule, this is the oxygen atom, these are the two hydrogen atom. Here also you know that there is a great difference between the electronegativity of the two atoms. So hydrogen will attain a positive charge, oxygen will attain a negative charge, as the shared pair of electron will shift towards oxygen. Now if we draw those arrows, it will be from positive towards the negative, from positive towards the negative. So the resultant dipole will be here somewhere. Clear? Similarly, if I'll take the example of BeF2 molecule, this is Be, this is beryllium, this is fluorine, this is another fluorine. You all know that fluorine will be negatively charged, Br will be positively charged, and the arrows will be like this. So the resultant dipole will be nowhere. Why? Because they are equally being pulled on both the sides. So I hope you have understood about the polarity of the bonds. Now children, next I am starting with hybridization. Now what is hybridization? Hybrid, you all know, must be a mixture of something. Here we are talking about the mixture of orbitals. So what is hybridization? It is the process of intermixing of atomic orbitals of slightly different energy so as to redistribute their energy and result in the formation of new set of orbital of equivalent energy and shape. That means here the orbitals which are having slightly different energy, they combine with each other and then redistribution of energy takes place and result in the formation of new set of orbital which is having equivalent energy and shape. Now there are certain important features of hybridization. See, number one is the number of hybrid orbitals formed will be equal to the number of atomic orbitals that gets hybridized. That means if two atomic orbitals are hybridizing, then two new hybrid orbitals will be formed, and so on. Number second, the hybridized orbitals are always equivalent in energy and shape. That means when the orbitals are redistribution of energy is taking place, then the orbitals will have equal energy and shape. Now number third is the hybrid orbitals are more effective in forming stable bonds than the pure atomic orbitals. That means if in case hybridization is taking place, then there will be more stability of the molecule. Number fourth, these hybrid orbitals are directed in the space in some preferred direction to have minimum repulsion between the electrons. So they will provide a particular geometry to the molecule. Now coming to the types of hybridization. Now children, depending upon the orbitals that are involved in the process of hybridization, it is of many types. I am starting with the basic one, the first one is sp hybridization. Now what is sp hybridization? In sp hybridization, one s orbital is involved and one p orbital is involved. So an example of a molecule which is showing sp hybridization is BeCl2. Now what happens in BeCl2? See, beryllium. What is the atomic number? It is 4. Configuration will be 1s2, 2s2. Total 4 electrons. Now what happened in the ground state? If we see, the outermost shell is 2s. In 2s orbital, 2 electrons are present. But see, you have to remember, in order to form a covalent bond, there should be a single electron. That means the unpaired electron should be present. This is the ground state. In the ground state of atom, paired electrons are present in this orbital. Now as I told you, for the formation of the covalent bond, unpaired electrons are present. Unpaired electrons are required. So what will happen? In the excited state, one of the electron from the 2s orbital, this electron will jump to the higher orbital. Now which one is the higher orbital? It is 2p orbital. This electron has jumped here. Now this electron jumping is possible only when the two orbitals undergo hybridization. So this s orbital and one p orbital are involved in the process of hybridization. So this type of hybridization is called sp hybridization. Now what will happen? This s orbital of beryllium will you can say overlap with the p orbital of chlorine. Similarly, the p orbital of beryllium will also overlap with the p orbital of chlorine and the bond formation will take place. So such hybridization is called sp hybridization.